welcome. So today I'm going to be giving an introduction to logic gates, which are sort of the building blocks for a lot of the theory of computer science and especially computer hardware. Okay, so computers need to talk to each other and they need to talk to themselves, right? They need some kind of language and some kind of internal way of representing data to themselves. Okay, so a computer needs to speak somehow. It needs to, be able to express thoughts. But it doesn't do this using the language that we're used to, right? It doesn't, on some very fundamental basic level, a computer doesn't speak with words and with punctuation and in complete sentences. A computer, somehow it just uses numbers. It somehow it represents all of the data that it needs using numbers. Okay. So you might think that it uses the numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But actually, if you really break down a computer and look on the most basic hardware level, really a computer only deals with zeros and ones. Okay. So, this is kind of conceptually important. Dealing with zeros and ones is a lot simpler than dealing with 9 or 10 different digits, because when you're trying to build a piece of hardware that actually realizes this form of communication and this form of language, you only have to worry about two things: a 0 and a 1. Okay, so what does this mean? I mean, maybe I should say this in a bit more detail. So if you think about a computer, right? A computer, if you ever looked at one, there's a bunch of parts, right? So maybe this is the mouse, maybe this is the keyboard, I don't know, maybe this is the graphics card, maybe this is the processor, this could be the monitor, etc., etc., etc. So it's a bunch of components, but they don't just live in isolation, right? There's a bunch of wires, and excuse my terrible drawing of a bunch of wires, but there's a bunch of wires connecting them, right? And in order to use a computer, you have to plug in a computer. So these wires, they're not just wires, they're wires that carry electric charge. Now, if you look closely at these wires and what they're doing, these wires for a computer, for the purposes of a computer, have two different states. So one state is a high voltage state, and one state is a low voltage state. And these are sort of opposites of each other, right? I can either put a lot of electricity into a wire in the high state, or I can put not much electricity into the wire in a low state. And this is important because, as I said before, computers use zeros and ones to communicate. And computers communicate across these wires. So there's two states, high and low. And so a high state is interpreted as a 1, and a low state is interpreted as a 0. Now, if you want, you can just conceptually think of this as, a 1 or a high state as being on, and a 0 or a low state as being off. Right? So instead of thinking of the wire as being, a high voltage wire or a low voltage wire, you can think of the wire just being turned on, as in electricity is flowing through this wire, or being turned off, which means that no electricity is flowing through this wire. Okay. So this is sort of the hardware implementation of this idea of zeros and ones. And this is sort of how a computer communicates using these different electrical states in these wires. Okay. Now, one important thing, when we use a computer, we want a computer to be able to handle kind of complicated things. We want to be able to handle language, we want to be able to handle pictures and videos and all kinds of complicated things. So a computer has to be able to encode all of this stuff into just zeros and ones, right? On your hard drive in your computer, all your data is just stored as zeros and ones. And the computer picks some clever encoding method to make the storage efficient. So, for instance, if I look at a piece of computer code, so this is just a simple piece of computer code that says the word hello in C++. So all of the characters in here, right, there's a bunch of different characters. There's all these letters, there's all these extra symbols. Well, the computer, the computer sort of needs to understand the alphabet in order to even make sense of this. And it also needs to understand these extra characters, but let's just focus on the alphabet for the time being. So how does it do this? Well, if you think about it, every character can just be assigned a different number, right? So A could be given the number 1, B could be given the number 2, C can be given 3, and so on and so forth. So a computer, instead of writing the letter I, could just write the number 9. And instead of writing the number n, could just write the number 14. And so it can sort of read off of these different numbers and make sense of them using this dictionary. Okay. Now, since we said everything has to happen with zeros and ones, you can't just reduce to this case where I'm looking at a bunch of numbers. I have to encode these numbers into zeros and ones. And so we do this using what's called the binary system. So some of you may be familiar with this. I'm going to talk about this in a bit more detail a bit later in this course. So for instance, 1 can be represented by 1, 2 can be represented by 1, 0, 3 is represented by 1, 1, 4 by 1, 0, 0, and so on and so forth. So this is the binary number system. And basically to every positive number, I can associate a unique sequence of zeros and ones. Okay. And right, I mean, the whole point is that 2 digits are now better than 10 digits because the computers that we work with, the way we build them, they just have 2 states, a high voltage and a low voltage, an on and an off. So this kind of encoding scheme is much more useful for us. And the same sort of idea works for pictures and videos, etc. Right? So I've told you how to kind of encode text, well, roughly, in terms of binary numbers. But if I look at a picture, I can decompose each pixel, which corresponds to a different color, into some binary number. And you can do this with videos, you can do this with documents, PDF files, programs, anything. Okay, so anything on a computer, really, can be encoded into zeros and ones. Otherwise, it wouldn't be on the computer, and you couldn't use it. Okay, so let's think more about how computers work. So schematically, what's happening? Well, I have some kind of input. So for instance, I may have a keyboard and I may have a mouse, and these give me different ways to input data into a computer. And then I have, well, the computer. I mean, I have some processor, I have some circuit, some chip that does the work. And then after doing the work, I output all the work that I've done as the computer onto a screen, for instance. Or, it could be anything. If I'm a microwave, then I input some numbers into the panel, and then it outputs a bunch of heat for a certain amount of time. You get the idea. But so in this setup, how does this work? I mean, if I put in 3 plus 4 into this keyboard, okay, then this 3 plus 4 sort of travels to the processor. The processor thinks, it knows how to do addition. There's some circuit inside that does addition. And so it thinks, and then after thinking, it produces the number 7 and outputs it on the screen. Okay, so this is roughly, this is a very simple example, but this illustrates how the workflow of a computer works. You give it some input, it does something with the input, and then it outputs something. So the complicated bit is really what's going on in here, right? I mean, this is the interesting part. This is like where the computation, if you will, takes place. And if you zoom in, I mean, if you really sort of carefully understand how these things are built, well, it's not just one single thing. I mean, it's millions and trillions of different things happening on the surface of the circuit board. And so essentially what you're doing is you're breaking down the process of computation into a bunch of tiny, tiny, tiny steps. And in a sense, the tiniest step, so okay, this is supposed to be zooming in on some piece of this circuit, and the tiniest steps are really in some sense these things which I'm going to call logic gates. So logic gates are these little symbols here, and logic gates are these sort of mini machines where you put in some inputs and then they spit out some outputs. Okay, so this course, I mean, at least this session is going to be dealing with these logic gates and thinking about them in more detail. So, right, okay, I want to give you first the simplest example of a logic gate. And so this is called the NOT gate. Now, maybe one thing which I should go back and say is that, the input, I mean, I told you that computers only speak to each other using zeros and ones, and they only think in terms of zeros and ones. So this input is somehow going to be a bunch of zeros and ones, right? So 3 plus 4 is going to be encoded somehow and given to this computer as a string of zeros and ones, which includes some instructions. So a logic gate is going to be some machine which takes as input a 0 or a 1 and then spits out either a 0 or a 1, right? Because this is the only language that a computer understands. So the simplest gate that you can give is what's called the NOT gate. So let's see how a NOT gate works. So if I give it, I should say that for all of these gates, the input always comes in from the left and the output is always going to go out into the right. So there's left to right is the direction that we choose by convention. Okay, so if I give in a 0 into this NOT gate, in other words, if I have a wire connected to this NOT gate and I don't put any electricity into it, then this NOT gate outputs a 1, which means that the wire coming out of the NOT gate is now charged. Okay, and then the opposite is true. If I put in a 1, if I put in a charged wire into this NOT gate, then a 0 comes out, which means that the wire going out of the NOT gate is not charged. And what this means is that essentially the NOT gate is, it's sort of flipping whatever you give it. If you give it a 0, it gives you a 1. If you give it a 1, it gives you a 0, which is sort of why it's called the NOT gate, I should say. And the NOT gate is always drawn in this notation. So you have a wire coming in, and then you have a triangle, and this triangle is pointing to the right. And on the tip of the triangle, at the point, is a tiny circle, and then a wire coming out of that circle. So whenever you see this symbol, and a wire coming in and a wire going out, this is a NOT gate. If you see 2 wires going in here, then somebody messed up, because that's not how a NOT gate works. Okay, so this is the simplest gate. Let's go on to this, maybe the second simplest gate. This is called the AND gate. So the slogan is that the AND gate will output 1 only when the first input wire and the second input wire are both on. All right, so what does this mean? Well, if you look at the AND gate, it looks a bit different from the NOT gate. Why? Because there are 2 inputs going into the AND gate instead of 1 input. Right, the NOT gate takes in 1 thing and spits out 1 thing. The AND gate takes in 2 things and spits out 1 thing. Okay, and again, the only thing I can feed these things are 0s and 1s. So, since there's only 2 inputs and there's only 2 numbers, there are 4 possibilities that I can give this AND gate. There are 4 possible inputs. So why don't we go through each one and see what happens. So 0 and 0 go into the AND gate. And now if I look at the rule, well, the AND gate outputs 1 only when the first input wire and the second input wire are both on, or in other words, are both 1. But in this case, neither of them are. So the AND gate spits out 0. In other words, the wire coming out of the AND gate is not charged, or has low voltage, if you will. The same thing happens if I give it a 0 and a 1. Right? Both of these wires need to be on for this wire to be on in the end. Okay. And again, the same thing happens with 1 and 0. Right? Nothing's changed. I still haven't given it 2 input wires that are both on. But on the other hand, if I give it 1 and I give it 1, then the AND gate spits out a 1. Right? And if you look at this sentence, you can sort of see what's going on, right? The AND gate will output 1 only when the first input wire and the second output wire are both on. This is why it's called AND. Okay, so I'll give you a couple seconds to look at this and digest it before moving on. Okay. So now let's go on to the OR gate. So this is the third gate that I'll introduce. Okay, so this looks sort of similar to the AND gate. So the AND gate, let's take a look at it again. The AND gate was drawn using it's almost a square except for that the right side is curved instead of being sort of squared off. The OR gate sort of looks like an AND gate except that both sides are now curved and this curve is a bit more pointy. So this is how you draw an OR gate. If you see a gate that looks like this, it should have 2 wires going in and it should behave like one of these. Now the OR gate will output 1 when either the first input wire or the second output wire are on. Right? This is why it's called an OR gate. So the AND gate, you needed both wires to be on in order to get a charged wire coming out. But for an OR gate, you only need 1. So just like we did before, let's go through all the possibilities and see what they give us. So 0 and 0 still give 0. Right? If neither of these input wires are on, then my output wire is not going to be on either. On the other hand, if I give a 0 and a 1, then now one of these is on. So now the output wire is allowed to be on. So this OR gate takes in a 0 and a 1 and spits out a 1. In the third case, right, the third case is similar to the second case. One of my wires is on, one of them is off, but all I need is for one of them to be on, and so I spit out a 1 again. And in the last case, I have two ones. And I only needed one of these things to be on in order to spit out a 1. So the output wire coming out of this OR gate in this case is a 1. Okay, so you can think of an OR gate as a much less strict version of an AND gate. Right? An AND gate requires two things to be on in order to turn on, but an OR gate you only have to give one. Okay, and I'll give you a couple seconds to digest this one. And if this is going a bit quickly, don't worry. So you can always refer back to this video during the exercises, which are going to come after the video. Okay. So there's one more gate I want to describe to you before we move on and actually do some exercises. And this is called the exclusive OR gate, or XOR gate. Now this thing, it looks sort of like the OR gate. It almost behaves like an OR gate. But when we draw it, we put an extra line on the left-hand side. So it looks like an OR gate, but then you just put this extra line, and this is what distinguishes it from the OR gate. Now the XOR gate, the exclusive OR gate, it's sort of like the OR gate, right? If one of the wires is on, then it outputs 1, but only one of the wires are allowed to be on. So if two of the wires going in, as inputs to the exclusive OR are on, then it's not going to output a 1, it's going to output a 0. So again, let's go through each of the cases individually and see what happens. Okay, so like before, 0 and 0 gives us a 0, right? Exactly one of the input wires have to be on, and in this case, neither of them are, so we get a 0. In this case, one of them is on, and exactly one of them is on, moreover, which means that the output wire coming from this XOR gate is a 1. If you look at the third case, 1, 0, the same thing happens, right? I put in a 1 and a 0, exactly one wire is on, so my output is 1. And the last case is the case where both of these wires are 1. Now in the OR gate case, this was enough to turn this output wire on. But exclusive OR is programmed so that only one of these wires is allowed to be on at one time. And so if both of them are on, then I'm not going to turn on my output as an exclusive OR gate. Okay. So I'll give you a couple seconds to look at this one and digest what it does. All right, so let me go back and just review all the gates that we just went over. So there was the NOT gate, which flips 2 bits. There's the AND gate, which outputs a 1 only if both of the inputs are 1. There's the OR gate, which outputs a 1 regardless of how many 1s there are. It's just as long as there's 1, then it outputs a 1. And there's the exclusive OR gate, which sort of looks for cases where there's exactly one given as an input to this gate. Okay, so now it's your turn. So now if you end this video and you look down further on the page, you'll see a couple exercises. So take some time, go through these exercises, and really try to understand what's going on. And then I will see you in the next video.